Hello, today we'll be talking about C2F2, otherwise known as difluoroacetylene. We'll first talk about the Vesper diagram, but before we do the Vesper diagram, we need to figure out how many valence electrons there are in total in order to create the Vesper diagram. So you have 4 electrons from carbon, plus 2 times 7 electrons per each fluorine. That gives a total of 22 valence electrons. Now that we figured out the valence electrons, now we can draw the Vesper diagram, which is represented right here. The Vesper diagram shows 2 pi bonds between the carbon atoms, 1, 2, and then a central sigma bond between the 2 carbon atoms. The fluorines on each end each have their little electron pairs. This will give a total of 22 valence electrons. The Vesper diagram represents a linear molecular geometry, but the electron geometry for C2F2 is also linear, which means that the angles will be 180 degrees. The hybridization for a linear molecular geometry is SP, represented over here. Because the Vesper diagram doesn't give a 3D shape and lets us view as much as we would like to, we also got the Mollypod kit from lab and made the 3D molecule. So this will be C2F2 on a 3D plane. The 3D molecule shape allows us to see the sigma and pi bonds between the 2 carbon atoms. There's a pi bond over here, and the second pi bond's right here, and the sigma is in the center region. The 2 fluorine atoms and how they bond to the carbon atoms is represented on the edges. Down below, we use the MOLS viewer app to see the atomic orbitals and how they make up the C2F2 molecule. So one of the pi bonds between carbon is represented right here, and the second pi bond is represented right here. This again is the carbon-carbon pi bond, and then the center region represents the sigma bond between the 2 carbon atoms. Once again, there's 2 carbon pi bonds and 1 sigma bond. Now that we've seen the shape of C2F2 on the Vesper diagram as well as in 3D molecule, and we also observed the atomic orbitals, now we can move on to the energy diagram. As you can see below, the ground state of carbon is 2s2, 2p, 2. But because you need a full electron, a full 2p electron subshell, you will promote one of the 2s electrons plus energy to fill this orbital. In order to create the sp hybridized orbital, you would only use these 2 electrons, because you only need these 2. So these 2 will move on to represent and be represented right here, my bad. The 2p unhybridized orbitals right here will move over and be represented over here. The 2p unhybridized orbital represents the 2 carbon-carbon pi bonds. The sp hybridized orbital represents the cf sigma bond and the cc central region carbon-carbon sigma bond. Now that we've seen the Vesper diagram for C2F2 and we've seen the 3D molecule, the 3D shape, my bad, and we've also now seen the electron box diagram, we can go on to the contour diagram for C2F2. The contour diagram for C2F2 gives us a closer look at the bonding between atoms, and it also gives you a closer look into the pi bonds and the sigma bonds between each atom. As you can see right here, this region right here represents the sigma bond between carbon and carbon. The 2p unhybridized orbitals over here make up one of the pi bonds for carbon-carbon, and this one right here. These 2 together make up one of the pi bonds for carbon. These 2 up here make up the second pi bond for carbon. Right here you can see the atomic orbital, how the atomic orbitals interact. Carbon and fluorine interact this way to create a sigma and are bonded together by a sigma bond. And the same goes over here. The bonding between these two represent the carbon fluorine second sigma bond. Once again, the bonding angles for the for C2F2 is 180, which represents a linear molecular geometry.